Welcome back. This video is going to cover a lot of kind of interpretive issues around correlation coefficients. So hopefully you've already watched the video where I did more of the math, and then this one is just going to show you how it often gets applied. So I want to start with a very famous example called the Anscombe Data Set. So I guess Professor Anscombe published this, I think it was in the American Statistician, way back in the 1970s or so. And what he did was he created 4 data sets. So here are 4 data sets. And these 4 data sets have been rigged so that the mean of X is the same across all 4 data sets. So here's data set 1. And if you look at X bar, the mean of X is 9 in each of these 4 scatter plots. The mean of Y is also equal in all 4 data sets to 1 decimal place. So they're not exactly equal, but really close to being equal. The standard deviation of X is the same. The standard deviation of Y is the same in all 4 data sets to, say 1 or 2 decimal places. And I've superimposed the correlation coefficients on these plots using ggplot. So you can see my code over here. And notice the correlation coefficients are all identical. So the point with this is, if we were to look only at single number summaries, so the means of X's, the means of Y, standard deviations, and correlations, we would conclude that, oh my goodness, all 4 of these data sets should be about the same because the single number summaries are all the same. However, when we look at the scatter plots, we see very different stories. So in the case of data set 1, we have a positive linear relationship. Data set 2 has what we're going to call an inverted U-shaped relationship. It looks like it's a parabola. So X, as X increases, Y also increases to a point, and then Y starts to get smaller beyond that point. Data set 3 is really a positive linear relationship with one outlier that exerts a lot of influence on the best fitting line. And then data set 4 is kind of a strange one where all of the X's are the same value, but there's one outlier that makes this have a line that's the same as the others. We haven't talked about regression yet, but the regression estimates are also the same across these 4 data sets. So the moral of the story is you've got to look at your data. So I've been emphasizing this since the first week of class, but always look at your data. The other point that I want to make with this is it's, I think, a really nice example of faceting in R. So this facet wrap is what allows me to generate 4 separate scatter plots. These are called small multiples by Tufte. So really, really useful, powerful graphical technique to know about faceting. All right, so a couple things that you need to know about correlations. They're always between -1 and +1. And we denote the population value by the Greek letter rho. We use the little letter r as the statistics. So R is an estimator of the parameter rho. Now these correlations tell us 2 things. They tell us the strength and the direction of the association between 2 variables. So notice my language here. I'm calling it the association. I'm not saying how X causes Y. I'm just trying to summarize how much X and Y go together. So how much are they associated with each other? So values of 0 indicate no linear association. Positive values indicate a positive association. Negative values indicate a negative association. So here are various plots that capture the magnitude part of this. So when rho is very close to 1, you have a very tight relationship where there's X is strongly associated with Y, so larger values of X are strongly associated with larger values of Y. When rho is smaller, you can barely see the correlation in this picture, but I've rigged it so the correlation really is 0.2. You see a very weak association. One more thing. Correlation of 0 indicates no linear association. It doesn't mean that there is no relationship between x and y. So the classic example of this, if I go over to my document camera, is something like this. Let's say this is x and this is y, and maybe I have some points that look like this. And there is no linear association. I can't draw a line that captures this relationship. So no linear association. So rho would be about 0 here. However, there is the variables are not independent of one another. That's meant to be a y, not another x. All right, so the variables, but x not independent of y. It's just that the relationship is more complicated. It's some sort of quadratic function here. All right, so that would be an example where we have no linear association, but the variables are dependent on one another. Y very much depends on x in that example. All right, just a couple more terms that you need to know about. One is an ecological correlation. So an ecological correlation is one where we correlate rates or averages. And whenever you see rates or averages correlated, you should beware. So that correlation will overstate the strength of the association between the two variables. So to understand why this is the case, I've generated a scatter plot here that actually has a correlation of 0.36, and I'll make it a little bit bigger for you. The way I've generated this is that there's actually 6 different states. Let's say these are states, and so all the x's live in the x state, all the o's live in the o state, all the triangles live in the triangle state. And this would be the scatter plot if I had a random sample of people from each of these 6 states. Now what we often do is we go to an almanac or something and get the average education level in the state and the average income level in the state. So if I took all the x's and I averaged them, this would be the average of all those x's. If I took all the o's, this would be average of the o's. And so notice what's happened. When I take the averages, I get rid of a lot of the noise, if you will. You can think of that as noise. And the association between education and income appears to be much stronger. So the correlation here is 0.95 than it is if I had studied it at the individual level, because there's a lot of differences across individuals. Right, so again, the point is whenever you have correlations based on rates or averages, beware, because the correlation overstates the strength of the relationship. All right. A lot of what is on the next 2 slides I've already covered when I did the sort of the probability theory version of correlations. But let me just go over some of this again. So if I take z sub x is going to be the standardized value of x, z sub y will be the standardized version of y. So take x minus its mean, divide by its standard deviation. Likewise for y. We estimate this with the sample mean and the sample standard deviation instead of the population mean and the population variance, which we don't know. All right. So remember what I said last time, Pearson correlation is just the covariance divided by the standard deviations. We can plug in our estimators and we end up with the same result I showed you last time. The Pearson correlation is just the average, so we're going to add up the products of the z values divided by n. Now, I think this actually makes a couple things really, obvious, a couple properties important. So Pearson correlations are unaffected by interchanging the two variables. So the correlation of x with y is the same as the correlation of y with x. Why? Because multiplication is commutative. So whether I take x times y or y times x, I get the same number. Another property that's really important to note is that I can replace x with a linear combination of x, and this value remains unchanged because when I take a linear combination of x, that same linear combination applies to the mean of x, and the constant, the multiplicative constant affects the standard deviation. So the additive parts go away. Maybe I should scribble this if you're not convinced. So let's go over here. I replace x with, say, x tilde, which is equal to ax plus b. So I've taken a linear combination, like maybe x is measured in degrees Fahrenheit, x tilde is measured in degrees Celsius. So I've just converted this to a different set of units. Or maybe x is centimeters and x tilde is miles. So again, I've taken a linear combination of this. So what I'd like to note is the expected value of x tilde is going to be a times the expected value of x plus b. The variance of x tilde will be, well, a squared times the variance of x. So let's go find z at x tilde. So z at x tilde will be x tilde. So let's go drop in, well, maybe I'll write all the steps out. So this is x tilde minus the expected value of x tilde divided by the square root of the variance of x tilde. So that's our standardized value of x tilde. Well, let's go write in all the stuff. So instead of x tilde, let's go write that in terms of x. So ax plus b. And then let's see, what is the mean of x tilde? So this is going to be minus a times the mean of x. So that's e at x is just the mean of x, minus b. And then I have to take the square root of the variance of x. So this is going to be the square root of a squared times sigma x squared. Well, notice minus b cancels out, and I'm left with, I can factor an a out, so a times, what do I have here? X minus the mean of x. And down here I have, well, what's the square root of a squared? It's the absolute value of a times sigma sub x. The a's cross out, and I'm left with x minus the mean of x divided by the standard deviation of x. And so, but one minor point, I assumed that this constant was positive. So that absolute value, the absolute value of a positive number is the number. So this is just a, since a was assumed positive. So those two cross out. If a were negative, then what happens is the sign flips. But the point I'm trying to make here, this is equal to zx. So if I transform my x to different units with this linear transformation, my standardized units remain the same. All right, so if I replace x with a linear combination, nothing happens. If I change y to a linear combination, nothing happens. And so the correlation is unaffected by a change in units of either of my variables. I am going to mention something from the future. So we're going to talk about confidence intervals and hypothesis tests in this class later. I'll just mention that there is a function in R, core.test, which will allow you to do hypothesis tests and also produce confidence intervals when we get there. All right, so that's it for my my unit on interpreting correlation coefficients.